Every single time you stream a song, fire off a text, or watch a video on your phone, there's this unsung hero working like crazy in the background to make sure it all just works. Well, today we're going to pull back the curtain on that hero, the LTE Radio Link Control Layer, or as we'll call it, RLC. I mean, have you ever really thought about that? Your phone's moving, right? The signal is bouncing off buildings, there's interference everywhere. So how on earth does your Netflix stream not just completely fall apart every time your signal so much as flickers? Well, the answer is all in the incredibly clever engineering of this RLC layer. And this slide just perfectly captures the whole problem. See, down at the physical level, the airwaves are pure chaos. Just a mess of scheduling gaps, errors, jitter, you name it. But way up at the top, your apps, they expect total ordered calm, a nice, smooth, predictable stream of data. RLC is that magical translator sitting right in the middle, turning that chaos into calm. So let's dig into that a little more. Let's talk about the villain of our story today, radio chaos. It's just the natural state of things for wireless communication. And honestly, without a really powerful defense against it, our digital lives would be basically impossible. Most textbooks will tell you that RLC does things like segmentation and retransmission. And yeah, that's technically true, but it kind of misses the whole point. The real mission of RLC is to be a shield. Think of it like a shock absorber. It takes all the bumps and jolts from the radio so that the layers above it, the ones handling your internet packets, they have no idea that chaos is even happening down below. And that brings us to the hero itself, the shield. So let's take a closer look at how this thing is actually built and where it fits into the grand scheme of your phone's connection to the world. RLC has a very specific and very important home. It sits right above the MAC layer and just below the PDCP layer. And here's the best way to think about it. The MAC layer is all about super fast, short-term fixes. It has this mechanism called HARC. But RLC is responsible for the long-term, guaranteed reliability. It's the one that cleans up any mess that the MAC layer just couldn't fix in time. Now, RLC is not a one-trick pony. Not at all. It's more like a Swiss Army knife with a different tool for every single job the network needs to get done. And it does this with 3 completely distinct modes of operation. And this lays it out perfectly. First, you've got transparent mode, which is super simple. It just passes data through, mostly for system info broadcasts. Then you've got unacknowledged mode, or which is built for pure speed. It's perfect for things like video streaming. And finally, you have the real workhorse, acknowledged mode, or AM. This one is all about ironclad, guaranteed reliability for your most important data. So let's put the 2 most important modes head to head. Unacknowledged mode is what you use for stuff like voice over LTE or streaming video. It can tolerate a little bit of data loss, but it's super sensitive to delays. Acknowledged mode is the complete opposite. It's for your web browsing, your file downloads, all that critical network signaling. It absolutely cannot tolerate any data loss, and it has to deliver every single piece perfectly in order. This quote just nails the logic behind unacknowledged mode. Just imagine you're on a phone call and a tiny piece of audio data gets lost over the air. What would you rather have? A tiny, probably unnoticeable blip in the audio, or would you want the whole network to pause the conversation, to go back and resend that old data, making everything choppy and delayed? Of course you'd prefer the tiny blip. And that's exactly why prioritizes speed over absolute perfection. Okay, but what about when perfection is the only option? Well, that's where acknowledged mode comes into play. So let's pop the hood and look at the incredible feedback loop that makes sure your data gets through, guaranteed. Acknowledged mode is a full-blown reliability engine. It's amazing. On the left here, you see the transmitting side. It uses a transmission buffer and a retransmission buffer, basically keeping a copy of everything it sends out. Then, on the right, the receiving side has a reception buffer to carefully check and reorder everything that comes in. This entire system, which is managed by something called a sliding window, is what lets the network keep track of every single piece of data. So how does this feedback loop, it's called ARQ by the way, actually work? Well, it's really just a simple 4-step dance. Step 1, the sender sends out packets, and each one gets a unique serial number. Step 2, the receiver looks at all the numbers and spots if there are any gaps. Step 3, it sends back a status report, basically saying, hey, I got everything up to number 42, but I'm missing 43 and 44. And finally, step 4, the sender just dips back into its buffer and resends only the missing packets. Brilliant. And this right here is that conversation in action. Your phone and the cell tower are constantly talking to each other. That status report, or status PDU, is the absolute key. It is so incredibly efficient because it allows for what's called selective retransmission. We're not wasting precious airtime resending data that already got there just fine. It's a smart, surgical, targeted recovery. But of course, no system is perfect. Even this incredibly tough shield can crack under pressure or because of bugs. So, what happens when things go wrong? This is a classic, and it is so frustrating. It's called a window stall. Just look at the diagram. Packet number 10 is missing. Now, because RLC in acknowledged mode must deliver data in the correct order, it can't deliver packets 11, 12, or 13, even though they've arrived perfectly fine. The entire data flow just freezes, completely blocked by that one missing piece. It's why your phone can show full bars of signal, but absolutely nothing will load. And other real-world problems can be even worse. When your phone switches towers, that's called a handover, the RLC has to reset. That can actually trick your internet connection into thinking the network is congested, and suddenly your download speed just crashes. But even scarier are memory leaks in the RLC buffers on the cell tower itself. According to folks who work on this stuff, this is one of the top reasons that entire cell towers just crash. And here's another little secret from the field. Getting the RLC timers tuned just right is an incredibly delicate balancing act. If a timer is too short, you can get congestion and clog up the works. If it's too long, you get huge latency and stalled data. For network engineers, tuning these timers is this constant battle to keep that shield strong. So let's bring it all back home. At the end of the day, RLC is that essential shield. It stands between the chaotic, messy, lossy world of radio physics and the smooth, ordered world that your apps demand. It uses its different modes, its powerful ARQ engine, to filter out all that chaos, making sure your data gets through both reliably and efficiently. And that really leaves us with one final big thought. We've seen just how critical this shield is for the network we use every day. But as we start moving towards 5G, 6G, and technologies like augmented reality and autonomous cars, well, the amount of radio chaos is about to explode. The demands for both speed and reliability are going to be unlike anything we've ever seen before. So the big question is, what is the next generation of this shield going to have to look like to hold strong?